Okay, so this week what we're looking at is branch connections. And in this set of slides, obviously we'll learn about what branch connections are, first of all, and we'll also have a look at things like how to set up a branch connection, and then ultimately how to set up a tunnel. Now, because I've got one screen, what I'll do is I've got Teams on my phone, so if anybody does want to ask me a question, you can just obviously give me a shout, or just ask me over the audio, or if you want to type something, you can type a message in, I'll be able to see it on my phone. All right. So basically, we're going to look at remote access connections. We're going to look at PPPoE, which is basically how to run PPP over Ethernet to allow for an end-to-end connection over Ethernet. And we'll look at VPNs. We'll look at how to create a GRE tunnel. So we'll look at the benefits of tunnels, and we'll look at creating a tunnel, and also how to troubleshoot it. And then we'll look at BGP. And BGP is the kind of protocol that's used out on the internet, if you like. It's to communicate with other autonomous systems. So you've learned about, obviously you do EIGRP and you do it within one autonomous system that you've got control of. But what if you want to connect that autonomous system to another autonomous system that you don't have control of? It's BGP that does it. Okay, so the first area in here is we're looking at remote access connections, what a remote access connection is and how it can be defined. So we'll look at the different types of broadband connection. Now, we kind of touched on these earlier in earlier chapters, so this will be dead straightforward. So a cable system is still quite heavily used, although they're being replaced now by fibre. But if you're in some areas of the country and you're with Virgin Media or whoever, you might still have a cable system that uses coaxial cable to, transfer your TV signal and your broadband signal. They use hybrid fibre coaxial, so it'll be fibre so far and then coaxial thereafter to give you the high-speed transmission of data. But it can also carry internet access, cable TV, and your phone service all in one. What do you need to have for cable? Basically two types of equipment. One to send the signals upstream and downstream. So you need a cable modem termination system. And you'll see here, that's at the head end. So that's at the cable provider's end. And then at the subscriber end, at your end, you need a cable modem, something that would obviously terminate that signal coming from the CMTS and then distribute it into your house for your TV and your broadband and your phone. Okay, so that was a brief overview of cable modem. We'll look at DSL. DSL originated for over 20 years ago now, the first kind of DSL, and before that, we just had dial-up. And if anybody is old enough to remember that, how hideous that was. You had to make sure nobody else was on the phone, and then while you were on the internet, at your lightning fast 56k or whatever speed you would get at maximum, nobody else could use a phone system because basically it used the phone system in your analog. It was an analog phone system, so there had to be some kind of digital to analog converter built into the modem, and your digital signal was carried via audio means down the line. That was until the advent of DSL, and basically DSL, you can see that there was a whole bandwidth available, and the telephone system only used maybe up to 4K of that for the audio side of it. So you had all this kind of frequency that was available on the line. The capability was there on the line if you changed it to a digital line. So basically, digital subscriber line is what it stands for. It gives you high-speed connections over the copper wires that were originally there. So it used the existing infrastructure in terms of the wiring. You had two main types: asymmetric, which means that's probably the most common type. You've got a faster download speed than you have with your upload. And if you do any kind of speed tests, you'll find that that's the same. Now you'll get a quicker download speed than your upload speed, because your upload speed doesn't have to be as quick as your download speed, obviously, does it? So that's why asymmetric came about. There's also symmetric DSL, maybe if you had a connection between two buildings that were far apart. Excuse me, you might use symmetric because it would be the same amount of data flowing from one into the other. And for ADSL, your local loop, you can't really have it. And I don't know why it's such a funny amount. I don't know why. It's 3.39 or 5.46. I don't know why that's kind of arbitrary figure, but you can't be more than about 3 miles to your exchange, or to where the kind of systems are held. You might find it's in a green box near your house. It doesn't have to be down to the telephone exchange. But certainly in the advent of ADSL, obviously all the equipment was in the telephone exchange, and so if you were further than about 3 miles from the exchange, you couldn't get ADSL. So that diagram just basically shows you the plain old telephone system used up to about 4K, but you had all this bandwidth that was available, and that digital line took advantage of that. So what do you need for a DSL connection? Basically what you need is inside I always say it's a telephone exchange. That's usually how it's done. Even Virgin Media have got a presence in the telephone exchange. So usually most ISPs, that's where their presence is. It goes into the telephone exchange. So if you know where your local telephone exchange is, ultimately that's where your cables run to, and that's where the kind of that's where your kind of main point for joining the cloud is. So your DSL connection is set up between your customer premise. So you'll have your customer premise here, you have your DSL modem. So that's classed as your customer premise equipment. Where that then goes is obviously this maximum distance, and it goes into the provider's network at that point. And inside there, you've got some kind of transceiver that basically connects the computer to the DSL, and you've got a DSLAM, and I think there's a picture later on that shows you what that is. But it basically combines all the individual DSL connections into a high capacity link that comes from the ISP. So the ISP's link, whoever you're with, comes into this, what's called a DSLAM. And the DSLAM is just like a multiplexer almost. It takes all the individual subscriber lines and pulls them all together and joins them to the ISP. So although you might hear about, if you're on ADSL, then you don't share the line with anyone because it's your telephone line. You're not sharing your telephone line with anyone. That's true until you get to the exchange, and then you're sharing via the DSLAM. And that's where it all combines together. So yeah, in fact, it says it here. The advantage of the DSL over cable technology is DSL is not a shared medium. Each user has a separate direct connection to the DSLAM. That's correct, because that's where your telephone line runs. Your telephone line is private to you, and that's a single line that runs to your house, whether it's through the wires or whether it's under the ground in modern houses. But it connects to this DSLAM. But then the bandwidth is then shared from the DSLAM through to the ISP, because obviously there's multiple people joining this and then going out one line that's being given by the ISP. So there's a kind of an idea of what it looks like. That's the kind of equipment you would typically see inside the exchange or inside a kind of intermediate box that you might have in the street. And essentially that's what it looks like. It just looks like a kind of router, doesn't it? It doesn't look like anything major. So I just stuck these into the slide just to take away that mystique about what is this thing? It's another kind of networking device, isn't it? Wireless connections, there are different wireless technologies, of course. We had talked about the municipal Wi-Fi, and the municipal networks or Wi-Fi is like towns and cities have got Wi-Fi that's available in the town. Some countries have got that as well, and that's the main way of pushing internet to people's homes. It isn't because they don't have the infrastructure. So if you go to somewhere like Thailand or the Philippines or somewhere like that, where they don't have the telephone exchange and the subscriber line infrastructure, then this might be a way of pushing out the internet to, a kind of large community of people. So obviously you can see you've got internet at some kind of building, you've got some kind of backhaul node connecting to that, and then you've got the Wi-Fi that goes out to different access points that are scattered throughout a kind of built up area of a town or a city. You've also got cellular or mobile networks. Sorry, someone want to ask something there? No, all good. Okay. We've also got cellular. Obviously, you can use your phone to connect to the internet, and that's via the nearest, they call it cell tower, your mobile phone towers. So LTE it's called, so they don't class it as 3G, 4G or whatever. That'll be LTE category 10 or whatever will be equivalent to 3G or 4G, whatever. And these are the download speeds. You've also got satellite internet using locations where land-based internet is just not available. The only installation requirement is the antenna has to have a clear view towards the equator to get the satellite. So other ways of getting broadband connections. And there's different factors to consider when you're thinking of, what's the best broadband solution for you. Is it cable? Bandwidth shared by many users can lead to slow data rates during high usage hours. DSL is probably the same, to be honest, because at higher usage, the DSLAM gets basically slammed with people trying to access it. And so that is true as well, is the fact that you've got limited bandwidth that's distance sensitive. So if you live in an area that you're far away from the exchange or far away from an intermediate box, you probably find that your internet speed is not that great. So that's one thing to consider. You can get fibre to the home, which is obviously what this picture is representing, and that's what's happening a lot more now. Virgin Media have had a huge rollout of that fibre to the home. Certainly down where I live, down in Kilmarnock, about a year ago, they basically did every single street in the town. So every single street in the town potentially has got the ability to have fibre to the home. It's right at the end of the driveway of every home. With cellular mobile, coverage is often an issue. I'm just going to have a look at mine just now. Yeah, I'm down at 1 bar where I am just now. I'm in an area called South Craigs. I don't know if anybody's familiar with it. Right at the top of the town in Kilmarnock. So it's quite far out from the major, the city centre. Yeah, and right enough, I've got 1 bar on my phone, so it's not a reliable phone. So I couldn't rely on a mobile signal for my internet in this house. Where I live down nearer into the town. I could rely on it because I'm getting about 4 bars, maybe 5, and so I get a great speed, and I could probably rely on that. Alex is saying mobile coverage where I am is terrible. You have to wave your phone. Yeah. Are you down? Is it down just near Ayr? You are, Alex. I think I know. I think I know where you mean. I've visited a caravan site down near there when the kids were younger. I don't know what it's like trying to get a signal down that way. Yeah, aye. Past Dobbies by any chance? Aye, Mabel. Aye, that's exactly where I thought. Yep. So Wi-Fi mesh as well is another one, and obviously satellite is expensive, limited capacity per subscriber, and the upload speed isn't great. So different broadband solutions. Probably the most common in UK are cable, DSL, now fibre to the home, and mobile, if you want to kind of include that. But most people tend to have one of these three. Okay, let's look at PPPoE then. So last week we looked at point-to-point protocol, and we looked at how point-to-point protocol is probably the most used out on the backbone of the internet, because with HDLC, that's only Cisco to Cisco. If you want to go to from a Cisco router to a non-Cisco router, HDLC is a Cisco proprietary protocol, so therefore you've got to use something else, and the something else we use is PPP. So PPP can be used on serial links, including those created with dial-up, analog, ISDN modems, any kind of point-to-point link, essentially. And ISPs often use PPP as the data link protocol over their broadband connections. ISPs can use PPP to assign your IP address, your public IP address. And obviously, if you do a what's my IP, you can find out what your IP address is that's been given to you. Or if you go into your router, you can see it that way as well. PPP, of course, supports the CHAP authentication, which is a bit more secure because it does, remember, it does the challenge authentication. However, Ethernet links do not natively support PPP. So how do you then get an end-to-end connection with PPP? You use PPPoE, and basically that takes you from your DSL modem to a host, and of course, same at the other end. You need this PPPoE to make it happen, to make that PPP connection from end to end, if you like. And you can see here, PC1 connects to a DSL modem. If it was a legacy dial-up scenario, PC1 reaches internet through the cloud by using a modem. But the same thing applies if you're going through a router or whatever. You would need the PPPoE to have the end-to-end connection. So basically, PPPoE, it creates a tunnel over an Ethernet connection, and basically what that allows is it allows the PPP frames to be sent across an Ethernet cable to the ISP from the customer's router. And you can see here, obviously, it's been packaged up, and you've got the PPP going across the internet, but it's come from the Ethernet. So how do we configure PPPoE? This is something that you will have to do for the practical. It's not that difficult. It's just knowing what are the main things that you need to do. Basically, the first thing you have to do, and just before I kind of move on to this, remember that for the practical, what I will do is I will do 2 sessions, because there's 2 main parts to the practical. I will do 2 sessions with you, and I'll go through all the commands, all the things that you need to know, and practice them with you in 2 different sessions, so that you can record it, obviously, and go back and replay it if you're not sure. But it also, what it will do is it will make sure that all those commands are fresh in your mind. Okay, so it's good to understand what's happening at the moment, but in terms of the practical side, don't worry about having to remember these in a pressure situation. It won't be like that. You'll have weeks and weeks to complete your practical. And prior to me setting the deadline or to giving you out, I will give you practice on what you need to do. So basically what you have to do is you have to first create the tunnel by creating a dialer, an interface dialer, it's called. So basically what you do is you give it any number you want. Obviously, you have to take cognizance of what number you've used. But what you do is you say interface dialer could be 1 or 2. They've used 2 here to show you that these numbers can be different. So interface dialer 2, it could be 2, it could be 9, it could be 200, it doesn't matter, right? You then say on that dialer, I want encapsulation PPP, and I want the IP address to be negotiated. Okay, so you just use those commands, and the IP address will obviously be, oh, am I still there? Yeah, sorry about that. I thought the signal had dropped there. I just heard a doodle-doo. Okay, let's go back to the commands again. So interface dialer, say interface dialer 2, encapsulation PPP, IP address negotiated. So that's to allow the IP address just to be negotiated. There's a chap hostname and a chap password, and you can just see the hostname is Fred and the password is Barney, right? Again, could be anything. So that just means for the ISP router, the username is going to be Fred and the password's Barney. Okay, now this bit here, can anybody tell me what an NTU is? No, don't see anything on the chat. Anyone? MTU? Yep, MTU. Maximum transmission unit. Yep, perfect. So the maximum transmission unit, can anybody tell me for Ethernet what it usually is set to by default? There's usually it's usually a round figure. It's not the figure that's shown there. So the MTU for Ethernet, typically? Anyone? Hazard a guess? Not quite. It's 1500. Usually the MTU is set to be 1500. And if you check on your router, you'll probably see that the MTU in there will be 1500. But it can be set to anything. It just basically says this is the maximum transmission unit. This is the size of the maximum size of a packet. So if you get a packet that's bigger than that, usually it means that there's something has happened. There's some kind of corruption has happened. You don't get me wrong, you can set the MTU to be any size you want. You can push more data more quickly if you've got a line that you know is secure and you know that it's robust. However, you would need to make sure it's 1500, or say you set it to 2.5. You need to make sure it's 2.5 everywhere, or else packets start getting dropped. So usually the agreed standard is 1500. Now, because we're using PPP-oE, PPP-oE is going to add some extra header information onto the packet. Now that's going to make the packet bigger than 1500. So what we have to do is we have to say, we have to make the MTU for this 1492. That's something you're going to need to do in the practical. Now, by making it 1492, you're giving it 8 bits, 8 bytes to be used for the PPP-oE headers. Okay, so you then just say dialer pool 1, no shutdown, and it brings it up. Now, this dialer pool basically is you can set who is allowed to bring up that line and who isn't. So in your interface gigabit that's going to connect to the internet, you say no IP address, PPP-oE enable, PPP-oE client dial pool number 1, just to match that. So we're saying traffic from the gigabit Ethernet 01 is allowed to bring up that, and then you say no shutdown. That's essentially the configuration. As long as you remember those stages, you configure the dialer, you make sure it's PPP, you say it's IP address negotiated, the CHAP, hostname and password for the security, take the MTU down a bit to allow for the bigger, or not bigger packets, but the headers that will be attached on to the packets. You then say, yeah, it's dialer pool 1 or whatever, as long as it matches this number here, no shutdown. You go into your interface that connects to the internet, no IP address, PPPoE enable, PPPoE client, dial pool number 1, match it to the dialer pool, no shutdown, that's it. That's basically saying this can now go out through that dialer pool, out through the dialer interface, and it's PPPoE. Because remember, PPP, it's like it's like a data link, isn't it? It's like a data link protocol. So that's why the IP address is all negotiated, because really PPP isn't really concerned about Ethernet. It's the Ethernet side that needs to deal with all that. So you can see here, you use interface dialer, and then number, whatever number you want. PPP chat is configured, hostname, password. The physical Ethernet interface that's connected to the DSL modem is enabled with the PPPoE enable command. The dialer interface is linked to the Ethernet interface with the dialer pool and the PPPoE client. Oh. And then remember to set the MTU. Okay, a few things to learn, but basically that's it. I mean, it's going to be the same when you come to do it in the assessment. It's going to be the same kind of scenario, and it's going to be the same kind of commands. Well, it is going to be the same commands essentially. You have to put in. Okay. Now, how do you then verify that it's working? Now, remember when you created your interface, you said interface dialer 2. So that's what you're looking for. So if you do a show IP interface brief, you'll see all your interfaces, and dialer 2 should be there. It should be given an IP address. It should be okay. It should be up, which means that the line is up and the protocol is up as well. You can do a show interface dialer 2 just to give it a bit more information. You can see the dialer is up and the line protocol is up. You can see the MTU 1492, that's important. And you should see the encapsulation is PPP on there. So show interface brief just to see that you've been given an IPv4 automatically assigned. The interface dialer verifies the MTU size and the fact that it's PPP encapsulation. You can do show IP route to make sure the route is going to go through, and you can show the PPPoE session, and that will basically display information about the current and active session that's currently going on. Troubleshooting. Again, with PPPoE, there's a number of possible causes. Basically, three main things. A failure in the PPP negotiation process. So the negotiation process falls down. And that can be something to do with the end-to-end. Isn't all PPP, maybe you've got an HDLC in there or something. Once that comes up, then the line should come up. So that's the first thing, make sure the line is up. The hardware side is up and it sees a connection. Then if you've got that up, but the other side is down, it's probably the PPP authentication process. And if you remember me struggling last week to try and get that working, remember? That was the authentication process. I had put in the wrong details for the username and password. Again, simple thing, simple mistake you can make. So check if you get an up-down, that's why. And one of the reasons is, and I keep going on about it, but it's so easy to miss, is to adjust the TCP maximum segment size, and that is your MTU. So you can use the debug command, debug PPP negotiation to verify the negotiation. 4 points of failure in the negotiation, no response from the remote device, the link control won't open, some kind of authentication failure, or the IP control protocol failure. And you can see if you debug PPP negotiation, you should see these things happening. State is open, chat, success, you get a response, you should get a success. You should get the IP address, obviously. You should get open, negotiated IP address, the route getting put in. So that should all be, that should be the kind of main things that you should see. Okay. And if you don't, then you obviously need to go back and check your commands. You can use the debug PPP negotiation. That's what I used last week. And you could see that's where it fell down. And that's what pinpointed me as to what the error was. But you should, again, see using hostname from interface chat, using password from interface chat. The response goes out, and you should see that success. And if you don't, like last week, like I did, it's something wrong with the username passwords. Right, I know they keep harping on about this MTU size, but it's obviously important, and it's obviously something you don't want to miss. Probably the chances are you're going to get asked questions on this as well in the assessment, because they do, I mean, that's how many slides is that they've gone on about this. It's a simple thing to know and to remember, but they're obviously trying to drill that into you and drill you into the reasons why you do that. So PPP supports an MTU of only 1492 bytes in order to accommodate the extra header, because you've got this PPPoE header, which is 8 bytes long, and that will bring you up to your 1500, which is your kind of max MTU. To check your MTU, just do a show running config, and you should see there under the interface dialer 2, there should be an MTU of 1492. There's an IP TCP adjust MSS. I don't think we've used this in the assessment, or no, I don't recall seeing it, but it's obviously something that it's important known. But basically that prevents TCP sessions from being dropped by adjusting the MSS value during the three-way handshake that goes on to that as well. Okay, there is a lab for configuring a router as a PPPoE client. I would recommend that you build it and try it. Like I say, it's not difficult. It's just getting used to the terminology that's in there. There's also a lab for troubleshooting PPPoE. So that will give you the kind of practical, but essentially that slide, see the slide that was there with about, there's maybe about 10 commands in it. That's all you need, because basically it's the same thing. You create the dialer, you create the information, then you post it on, set the MTU, then you put it onto the interface. That's it. So it sounds complicated, but it really isn't. It's just following those commands, following that same structure. Okay. Before I move on to VPNs, is everybody okay with that? Good, good. Okay, that's fine. So let's look at VPNs then. Now, before I kind of look into VPNs, essentially, in fact, I'll take us back one so it doesn't distract you. Basically, the VPNs, what they're doing is they're saying in here, yeah, you can have a private leased line. A private leased line will cost you lots and lots and lots of money. So an alternative might be, if you don't have the money, is to use the public internet. But in order to make things secure, to keep the conversation private, because you're on a public, you're on the public internet, then they recommend that you use VPNs. So you might know or recognize VPNs for other purposes, perhaps. But the main reason is to keep things secure. And that's the kind of idea. So it's a private network, VPN, virtual private network, created via tunneling over a public network, which is usually the internet. You can have secure VPN, so you can have the encryption being dealt with by IPsec, for example. But when people talk about VPNs, what they usually mean is virtual private network. So to implement a VPN gateway is necessary. It could be something like a firewall or a Cisco ASA device, or just a router. Router can do it. But if you're talking about a dedicated device that will do it, you're probably looking at maybe an ASA. If you're thinking about in a building, for example, and you wanted to create a VPN from a point to a point, you're probably looking at a dedicated device that's what its job is. So an ASA would be, it just looks like a router, to be honest, usually one in, one out. But that's what you can use, but you can use a router, absolutely fine. So basically what happens is you're going through a public internet to get to another site. So let's say we're up here, business partner with a Cisco router. They want to connect securely to the main site, create a tunnel. And essentially all the data passes down that tunnel. Anybody tries to intercept it, they can't get it because it's a secure tunnel, essentially. So why do it? Cost savings, that's what I said at the beginning, didn't I? So VPN enables organizations to use cost-effective, high bandwidth technologies such as DSL or any kind of internet technologies to connect remote offices to a main central site. It's scalable. Organizations are able to add large amounts of capacity without adding any infrastructure. You don't have to go and buy multiple leased lines to do it. You just use the public internet, use a VPN. It's compatible with broadband technology, so people working at home can use a VPN to get into the building. And I know there's a couple of guys here who are part of the tech team. I guess that's how you're connecting to the secure systems of the college via some VPN in. On my phone, yeah. Yeah, that's right. You can create a Raspberry Pi. If you want to create a VPN using a Raspberry Pi VPN project, it's good. Yeah, definitely. You can get apps now on your phone. You can download a VPN, pay a subscription, and you can use VPN on your phone, which is handy if you're in a public area and you want to do internet banking or something. If you're on a public network that's free and open, you don't want to be doing internet banking or anything secure like that. On a public network, you obviously want to switch on a VPN to be secure. So you can get apps like now for your phone. Okay, yeah, you can add security. You can use advanced encryption on authentication protocols along with your VPN as well to make it extra secure. So a site-to-site VPN basically connects one network to another. So a branch office network to a company's network headquarters. In a site-to-site VPN, basically the hosts will just receive normal TCP IP traffic, and it's from this kind of public-facing router to the other public-facing router is where the VPN is created. So it's created on that point-to-point link. But the client here is just Ethernet there. So it's Ethernet to the router, and then it's through a VPN in here, and then obviously the host at this end again would be connected via Ethernet. So, it's just when they're broadcast over the public internet, that's when it's tunneled. And that's used for encapsulating and encrypting the traffic. Remote access VPNs basically allow mobile users extranet traffic, and you can basically create that. The client initiates the VPN connection, and then they can connect securely in. Okay, and you can do that on individual hosts. You probably have to have some kind of VPN software or VPN setup done on your laptop or the machine you want to use to VPN in. So the client will be aware that they are VPNing in because they will have to physically connect to the VPN first before they can get access at that end. There's also dynamic multi-point VPN, and that's obviously for building multiple VPNs. It's like having a private cloud in the public cloud. Does that make sense? So if you've got multiple sites and multiple locations and you want to join them all together securely, but over the internet, you can do that. So you're using the public cloud, but what you're doing is it's all through VPNs, so it's all secure. So there's multiple technologies that allow that to happen. You've got next hop resolution protocol that's used for mapping the database of the public IP addresses for all the spokes. There'll be multi-point GRE tunnels, generic routing encapsulation. So there'll be a multi-point GRE tunnel interface to allow multiple tunnels. And you want to have some kind of encryption in there that will encrypt all the traffic to make sure that if anybody does pipe off your data, they can't do anything with it. Okay, GRE. See, before I look at GRE, I'm going to show you how easy it is to create a GRE tunnel, and then we can go back and have a look at how GRE works. Okay, so I think it's better if you see it, then I go over it, because I think because it's when you try and teach it as a concept, it doesn't scale well. So can everybody see the little network I've kind of pre-configured here? Now, I've got two versions of this that I've put into the team. What I've done with this one is I have connected HQ to ISP and ISP to branch, and that's working. That's pinging across. Now, I haven't yet created a tunnel, and that's what I'm about to do now, show you how to create a tunnel between HQ and branch. So effectively, your packets are still going up and across, but as far as the routers see, the routers just think they're going across a tunnel that's directly linked between branch and HQ. So you're effectively creating like a fake, that's why it's called a virtual private network. You're creating a fake tunnel that's tunneling between these two, and the data will pass through that tunnel. In reality, what's happening is you're having encapsulated packets that are going up here and across there, but the routers don't know that. They see it as the data is just going firing from one to the other. Okay, so the HQ link to the ISP link, 192.168.12.0 network. I think that's 12.1 and that's 12.2. Let me just hover over and I'll tell you. Yeah, 12.1. And up here, it's 12.2. Yeah. On this leg, we've got ISP to branch, and that's the 23 network. And again, 23.1, 23.2. So if I try and ping HQ to branch, you can see that it is successful. If I go into HQ and I go into command line, I'll just ping 23.2 just to show you. So ping 192.168.23.2. You can see that's happy, it's pinging that okay. So that's HQ, which is here, and it's going up and it's going across and it's pinging the branch interface here. So all I've done to connect that, I haven't even used serial connections just to make it simple, take away all the kind of complexity of that. All I've done is crossover cable, did all the network part, and I think, if I remember rightly, I just used RIP. Sure. So yeah, router RIP, you can see there. So just a simple router RIP with the interfaces, and I've got that network all talking. You need to do that first. You need to ensure that obviously your network is up and running before you start trying to add a tunnel in. If this is not functional, the tunnel won't function, okay? So let's show you how easy it is to create a tunnel. Basically, on HQ, what I'm going to do is I'm going to create an interface. So I'm going to call it interface tunnel. I'll call it 1. Again, it could be anything as long as you get the numbers the same on both sides. So interface tunnel 1, can you see what's happened? The tunnel has changed state to up. So as soon as I hit tunnel, it's creating my tunnel for me. So what I need to do is I need to say 3 bits of information. I need to say what's the source of the tunnel, what's the destination of the tunnel, and what's the tunnel's IP address going to be. That's all I need. Okay, so what I'm going to say is, I'm still in the tunnel interface, so I'm going to say, so tunnel source. Now, that's the interface here. So the source is here. Now, that's the fast Ethernet port, I think. Is that fast Ethernet? Hold on, I'll just minimize this to double check. Yeah, so it's fast Ethernet port. And on this side, because I need to make sure this side as well. Yeah, both fast Ethernet ports. I wanted to get it right because I don't want to end up troubleshooting. So tunnel source, fast Ethernet 00. Okay, so we're saying that the source of the tunnel is going to be here. Now, what's the destination of the tunnel? The destination of the tunnel is down here. So that's that port I've just pinged, which is 23, what did I say it was? What did I ping? Oh, 23.2 or was it 23.3? Hold on. I've got to get this right as well. Make sure this is right. 23.3 it was. 23.2 must be up here. Aye, 23.2 was up there. So in fact, I better just ping 23.3 just to make sure. Sure it's fine though. Okay, back into Packet Tracer. So my tunnel destination is going to be 192.168.23.3. This IP address here of the other end. So my source is here, the fast Ethernet port. My destination is here, the IP address. Obviously, you can't put the port because it's not local. It's okay to do the port if you're local. So it's the port, local port, and the destination IP address. Okay, you can see now what's happened. The line protocol has now come up. So our tunnel is up and running. One last thing we need to do is give that tunnel an IP address. So I've said the IP address of the tunnel should be 192.168.13.3. So 192. Oh, damn it, was on there. Right, IP address 192.168. 13.1, yeah, because it's here. I'm on HQ, aren't I? So the IP address for the tunnel at this end is 192.168.13.1, and then it's just going to be default mask. That's the tunnel created. So what did I do to create? Well, I created one end of the tunnel. What did I do to create that end of the tunnel? Interface tunnel 1. Okay. Tunnel source, fast Ethernet port. Tunnel destination, far end IP address, and then give the tunnel its own IP address, which is 192.168.13.1. That's that end of the tunnel created. All I've got to do is a similar thing on branch. So interface tunnel 1, tunnel change state to up. So again, the tunnel, because it's the same source, isn't it? It's the fast Ethernet port. Tunnel source fast Ethernet 00. Okay, and that brings that up. Tunnel destination. Now let's just double check this. I reckon it's 12.1, which is that port there, that IP address on there. So tunnel destination is 192.168.12.1. Okay. line protocols come up on the tunnel, the last thing I need to do is give that end of the tunnel here 13.3, give it an IP address. So IP address is 192.168.13.3 with a default mask. Now, our tunnel should now be up and running. So show interface tunnel 1. Just to have a look, see what's happening. Tunnel 1 is up. Its line protocol is up. It's connected. It's a hardware tunnel. You can see here, by default, I haven't specified it was a GRE tunnel. The default protocol, you can see tunnel protocol, GRE, tunnel transport, IP. So by default, it will be a GRE tunnel with an IP transport on it. Okay? You don't need to tell it otherwise. What else do we need to see? Tunnel source 23.3, destination 12.1, and the actual tunnel address itself is 192.168.13.3. Okay, so it needs to know the source, it needs to know the destination, but it needs to know what end, what is my IP address of the tunnel. So what I can do now is, let's see if I can get packets to go through the tunnel. So I'm on branch at the moment. If I ping the other end of the tunnel, which is 13.1, I should get a reply. So ping 192.168.13.1. Now remember, the first 1 or 2 packets might drop, and we're looking for exclamation marks. So you might see ... exclamation mark, exclamation mark, exclamation mark. That would be normal. So let's see. Exactly as I predicted. 2 dots and then 3 exclamation marks. The dots happen because, can MD tell me why that's normal?
It has to converge.
Sort of, yeah. It has to do the ARP lookup and all of that. And by the time it does all the ARP lookup, it takes a wee bit of time for that to happen. If I ping it again now, it'll be all 5 will be through. Usually you first find the first 1 or 2 drop out because it's a way doing the ARP lookup and it's a way resolving the IP addresses to MAC addresses and getting all that information. And by the time it's done all that, the first ping or the first and second ping might time out. But you can see the rest have come through, and then I've done it again and all 5 have come through. So my tunnel's up, my tunnel's running. I've done the ping from branch and it's now going through the tunnel. So basically what was that? Interface tunnel 1, source port, destination IP address, and the IP address of the tunnel itself. 4 commands on one side, similar 4 commands on the other. Tunnels up, and we're transferring traffic through that tunnel. So that's how easy it is.
What would happen there if you do a trace route?
If we did a trace route, it will. Well, let's have a look. Actually, trace 192.168.13. I'm guessing it's going to go directly through the tunnel. Yep. It's gone directly to the tunnel. So in reality, what's happening is it's going from branch to ISP and back down. So you would expect the trace to reflect that, wouldn't you? You would expect it to come up here, go via here, and then go back down here. But you can see the trace, what it's happened is 1 hop directly through the tunnel. If, for example, I said, if I wanted to go to trace 192.168.12.1, which is here, if I pinged that, so this is not me going through the tunnel, I would expect to see it going through ISP. Yeah. which it's done. So if you're using the tunnel IP address, the router just thinks it's going straight through the tunnel. So it's one hop. If I'm going to that IP address, i.e. not using the tunnel's interface, it goes up and across, and you can see it's 2 hops to get there. So that's a good question.
It did it in a quarter of the time.
One millisecond, and then that one's 4 milliseconds. So yeah, so the tunnel was faster, which is bizarre, really, isn't it? Can't quite. It's just arbitrary, obviously. It's all, these are just, that's maybe been an ARP delay or something. It doesn't look as if that's the case. Yeah, see, it just seems to be sort of random, those. Okay, so let's have a look at GRE tunnel. It's effectively, see, when I've taught this in the past, people have gone, tunnels, oh no, how do you get a tunnel? How do you create a tunnel? Oh no, it's really complicated. It's not. It isn't really complicated at all. And that's why I thought, I'll show you it. I'll show you how easy it is, how many commands it takes to get a tunnel up and running. It's no bother. So what I've done is, in the team site, I've given you 2 packet tracers. One is that scenario without the tunnel being created, so you can go through the commands and try and create the tunnel. The second one I've given you is with the tunnel created, so you can have a look at the commands if you're not sure, if you get lost. So there's 2 there. There's one before the tunnel, and there's one after the tunnel. So you can have a look and play about with it. Okay, so GRE tunnel, remember it's non-secure, but it's a site-to-site VPN tunneling protocol. Developed by Cisco, that's why it's the default one when you create a tunnel. Basically what it does is it manages the transportation of the, whatever protocol it might be, and the IP multicast traffic between 2 or more sites. And basically what happens is it will be encapsulated in the tunnel. So you can see there's your original IP packet. So you've got your IP and your TCP and then your data. So that's like the passenger protocol. What the tunnel does is it adds its own IP information and the GRE information as well. So it tacks that on to the original packet. So basically, you've got an encapsulated protocol, you've got an encapsulation protocol. Now that could be GRE, that's the default. That's the protocol that's used to encapsulate the data. And then you've got a transport delivery. How do you get that, across? And it's IP. That's why the tunnel needs an IP address at each end. So it's an IETF standard. Basically, if you look at the outer header, 47 is used in the protocol field to identify that it's a GRE tunnel. GRE encapsulation uses the protocol type field in the header to support encapsulation of any layer 3 protocol. So that's why ping worked, for example, when we were able to ping across the tunnel, because it's ICMP, isn't it? So it can use any layer 3 protocol. It's stateless. It doesn't include any strong security mechanisms within it. What you will need to do if you want to make it secure is to add something like IPsec. It does create 24 bytes of additional overhead for the tunneled packets. So every single packet that you send, you're losing 24 bytes of payload, if you like, because that's how much it takes to send the tunnel or to, create the tunnel and have this added bit at the front. So here's a similar scenario. Basically, 5 steps. I said there was 4. Oh, there's a 5th optional one, right? Okay. So you create the tunnel interface using the number. You configure an IP address for the tunnel. You specify the source. You specify the destination. That's it. they're saying a step 5 optional, specify GRE tunnel mode as the tunnel interface mode. Yeah, that's default. So if you don't specify it as being GRE, it will be GRE by default. So that tunnel mode GRE IP, remember when I looked at my tunnel interface, it did say GRE IP anyway. So, you know, that's kind of, I suppose it's kind of redundant. If you want to make sure that you're definitely using tunnel GRE with IP, then stick that command in, but by default, it's there. And basically, the source and the destination commands reference the IP addresses of the pre-configured physical interfaces. So, yeah, just like I had, if you had router 1 S00, you could either say S00 is the source, or 209.165.201.1 is the source. The destination is 198.133.219.87, and then of course you give your tunnel an IP address as well. So just similar to the example I had shown you there. Show interface brief will show you obviously just the brief information about, is it up, what IP address is it using. If you do show interface tunnel, that's what I did, and you can see that tunnel is up, line protocol is up, its internet address, IP address of the tunnel source, the tunnel destination, and the protocol and transport in there as well. You can also do show IP OSPF neighbor. If you were using OSPF, for example, when you create a new interface, that should create a new adjacency because it will be going over the tunnel interface. What I could have done there is, I didn't, but what I could have done was I could have put the tunnel in the tunnel network address, into RIP and get that to be picked up, because it just gets picked up as a normal interface. Troubleshooting GRE, very rarely does it go wrong. If your network was working before you created the tunnel and you create the tunnel with the correct commands, it will work. Only thing I've ever seen it not working is if the network wasn't working beforehand, in which case it would never work anyway, or there's been a misconfiguration when you set it up. Other than that, it just works. So what they're saying here, issues, the tunnel interface IP addresses are not on the same network. Of course, they've got to be in the same network. It's a point-to-point link, so they have to be in the same network. Show IP interface brief to configure that, or to confirm. The interfaces for the tunnel source and or the destination are configured with the correct IP addresses or are down. Oh, sorry, they're not configured yet. So again, if you don't configure it right, it's not going to work, is it? So make sure that's happening. Static or dynamic routing is not properly configured. And again, yeah, if it didn't work before because you haven't got static routes or you haven't used RIP or OSPF or EIGRP, then it's not going to work. And just make sure that the routes are in there. Okay. But usually, if your network is working beforehand, then you create the tunnel, it will work. That's usually, people go ahead and they create a network, then they put the tunnel in and go, it's not working. You go, okay, wait a minute, take the tunnel back out. Is it working? No. Well, that's why you have to have a working network first, then put the tunnel on. Take it one stage at a time. Obviously, I put my lab in, the one I created. There's a good lab in here. There's a packet tracer one for configuring GRE, and that will allow you to basically, you can see that there's an internet connection there. So between these two routers, it goes to an internet connection and then down here. But what you're going to do is create a tunnel directly across. So from PCA to PCB, they just think they're going through these two routers to get to there. In reality, what's happening is these two routers are going out over the internet and coming back. But it appears as if there's just a tunnel in there. There's a good one for troubleshooting as well, because things can and do go wrong. But with GRE on its own, like I say, in my experience, if you've got the network working and you configure it correctly, it will work. So, but what happens if it doesn't work? What kind of commands do you use? And obviously all the kind of debug and show commands it will teach you in here. And there's also one in here for a real lab for the real kit to show you how to configure a point-to-point link. You can do that one with routers, obviously, and that's kind of the way I've done it on my packet tracer. Okay, the last part of this then is around BGP. Now, BGP is Border Gateway Protocol. Basically, Border Gateway Protocol is it's used as the backbone of the internet to connect between different autonomous systems. So you're in charge of an autonomous system, so that let's say, for example, the college is an autonomous system. All the routers and switches that are in there are part of an autonomous system. They then have to go out on to their ISP, and they might want to be connecting to other autonomous systems. So how does that happen? Well, what are the routing protocols to allow that to happen? And it's Border Gateway Protocol. And you can see that the E there stands for external, because as we look into this, you would think it would be external, wouldn't you? You would think, well, it's external. It's not for this autonomous system. It's an external to my network, and it connects different networks together. You will see that there are certain instances where you might have different flavors of BGP, so an external and an internal. So let's look at the external first. So if we think about, first of all, what is an interior gateway protocol? An interior gateway protocol is something like EIGRP or OSPF or RIP or something like that. It's used to exchange routing information within a company network or an autonomous system. An exterior gateway protocol is used for the exchange of routing information between autonomous systems, such as ISPs, and Border Gateway Protocol is one of these exterior gateway protocols. I think there's a couple, BGP, and there's one called ISIS, which is a kind of older one, but Border Gateway Protocol seems to be the one now. So every autonomous system, if you've got an autonomous system, you'll have an autonomous system number, a unique 16 or 32-bit number, which identifies it on the internet. That's what Border Gateway Protocol uses to make its routing decisions. It's based on this autonomous system number, the unique autonomous system number. So external BGP, that's the routing protocol that's used between routers out on the internet that goes between different autonomous systems. There's also an internal BGP as well, and that's used between routers in the same autonomous system number, but that want to be seen outside of that network, if that makes sense, right? So if you've got two routers that need to be seen out on the internet, you would use internal BGP to communicate with them internally. And I've got a little diagram here, for example, down right at the bottom, where I've got autonomous system 1, it's got one router. Autonomous system 3, it's got one router. So you've got external BGP connecting these together. Now, autonomous system 2 has got 3 routers, router 1, router 2, router 3, that all need to be seen out on the internet. And so what happens is you've got internal BGP running on the ones that need to be seen externally. And it just means that the adverts for router 2, router 1, and router 3 go out via eBGP. Does that make sense? I think at first, when I first came across this, I was going, huh? why would you need internal BGP? But you only need internal BGP for the routers that want to be internet facing. So you wouldn't advertise, your private routers that make up your internal network, only the ones that need to be seen out on the internet. And it just means if you use iBGP, all of these paths are then advertised out to other autonomous systems. Okay, does that make sense before I kind of move on? Hopefully. Good, okay, that's great, Alex. Okay. So when do you use BGP? Basically, BGP is used when an autonomous system has got connections to multiple autonomous systems, and that's known as multi-homed. You've got to be really, really careful, because if you misconfigure a BGP router, it could have negative effects throughout not just your autonomous system or that link, but the whole internet. Because if it starts advertising things that are wrong or that are incorrect, remember, this advertises it out to the whole internet. So you've got to really, really be sure of what you're doing when you're configuring BGP out on the internet, because like it says, a misconfiguration of BGP could have negative effects throughout the whole internet. That's frightening, actually, isn't it? When not to use BGP. Now, to tell you in this Cisco slide, totally just, I don't know, this is great. But basically, they're saying don't use BGP when you've got a single connection to the internet. That's known as what's called single-homed. If you've got a single connection to the internet or another autonomous system, just use a static route. Don't use BGP. Just have a static route one way and a static route the other way. That's all you need, because what else would you need? But because it's important for you to learn BGP and important for you to learn how it works, it's saying it's recommended only in unusual circumstances to configure single-homed BGP. Guess what you're going to be doing in this course? Yep, you're going to be configuring single-homed BGP. And it'll be one of the things that you'll be doing in the practical at the end. I think there's one router goes off, or it's an ISP router or something. I can't remember what it is. You have to configure BGP on that. Excuse me, it's not difficult, but obviously what they're saying is it's usually used, BGP is used in this scenario. Now, you've got different autonomous systems, different companies, different routers all over the place, different ways of getting to different places. That's very complicated, obviously. And if you were just beginning to learn BGP, how would you even get your head around what's happening there? So what they're saying is, we're going to have a scenario where you've essentially got one router joining another router. Normally, what you would do in industry is you would static route one way, a static route the other way. That's it. However, because we're just learning, we're going to learn BGP on a single-homed network, but that's not usually how it's used. Okay. So, 3 common ways an organization can implement BGP. They can have it as a default route, they can have a default route and ISP routes, or they can have all internet routes. Now, all internet routes include the routes to every single autonomous system. It's over 550,000 networks. So be very careful if it's all internet routes that you want to set up. And that's what they're saying in the back of your mind. Always be wary of that. So basically, to implement BGP, it's very simple. You just say, just as you would on router RIP, router OSPF, router EIGRP, you just say router BGP, and then you give it an autonomous system number. You then specify the neighbors which are the BGP peers. So you say neighbor, the IP address, remote AS, the autonomous system number, and then you give the remote autonomous system number. So obviously you say, right, okay, the neighboring router I'm connected to, this is its IP address, and this is the autonomous system number that it belongs to. And you give it that information as well. And then you basically give it the network address to advertise. And it's a network address and the subnet mask as well. Essentially, that's it. And in terms of when you do the assessment, that will be kind of pretty much all you need to do, and just ensure that BGP is working on both ends. So here's a sample configuration. You can see there, it's a single home. So you've got one router here, joining to another router here. That'll be kind of similar to what you're going to be doing in the assessment. You can see different autonomous system numbers. So that's company A, whereas that's ISP. That's 65,000, that's 65,001. So on the company A router, you say router BGP 65,000. You see the neighbor is 209.165.201.1, which is that IP address. And you say that's a remote autonomous system 65,001. Easy. Then you say, okay, what network am I going to be advertising? Well, it's this network, this internal network here, isn't it? So it's 198.133.219.0 with a 24 mask, so it's 3255s and a 0. On the other end, it's kind of the same, but in reverse. Router BGP 65,001. Network is 209.165.201.2, which is obviously the other end. The remote autonomous system number here, 65,000. And then you say network, this time, network 0000. Now, why do you think it would be 0000 rather than specifying a network? Bear in mind that this is the ISP. Anyway, I'm just checking my text and checking the chat. No, nobody. Why would you say network? It's a default network, yeah. Basically, what you're saying is you're not committing to any particular network. You're just saying every network, because remember, the ISP is connected to the internet, so you don't know what networks are going to be coming through here. So you're just basically saying any network, and it just opens it right out. It's like, as you say, it's like a default network. It just opens it right out to everything because you're connected to the internet. Okay, so it's simple to set up BGP. You can see three commands on the ISP side as well. Dead easy. So how do you verify it? Show IP route, and you should see a B entry for BGP. You can show IP BGP, just like you can for show IP RIP, show IP EIGRP. And you can show the IP BGP summary as well. And you can see the kind of routing information that's going back and forward, and the neighbor adjacency that's there as well. So quite straightforward. There is a packet tracer that will allow you to configure and verify external BGP, and you can see obviously what's happening there. There's also a lab to configure that. Again, that's built with more the kind of router equipment that you would get in the lab, but you can build that in Packet Tracer as well. Okay. So basically, if I go back, we have covered quite a bit today actually. We covered different types of remote access connection. We looked at the different types of broadband. We looked at PPPoE. So what PPPoE was for, it basically allowed you to extend PPP right to an end user via Ethernet. So it's basically PPP, but it's over Ethernet, and we saw how to set that up. Okay, VPNs. We had to look at VPNs, site-to-site security, and we saw how to set up a type of VPN, which was the GRE tunnel, and we've learned about BGP in a single-homed network, and we can see how to set that up as well. Again, fairly simple to set up, nothing major in there at all. So I'm going to go back to stop sharing and just go back to my screen. So does anybody have any questions on that? I know there's quite a lot in there. I think the concepts are fairly okay, fairly simple. Certainly the commands, when you start to practice them, are fairly simple as well. And there's plenty of labs in there. There's 3 separate labs, one for PPPoE, one for the GRE, and one for the BGP. If you get in amongst them, I probably recommend you do that. You know, get time this afternoon. Alan had said to me that he wasn't going to start his class till after Easter, so you certainly got the time this afternoon to get into those labs and have a look at what they're like. I want to pull up, just in case anybody's still thinking about, you know, question to ask. What I was going to do was I'm going to pull up the schedule. A few people had asked me about it during the week. You know, where do we have to be? Because obviously this is the last lesson before the Easter break. Okay, I'm just going to share my screen again quickly.
Ian, I'm just going to say, you know, you mentioned a couple of times assessments. Are you talking about the exams, or is that something separate?
What I've been talking about is mostly the chapter exams and or the practical final, which I'll show you in a wee minute.